Hello and welcome to this film about isotopes. It's quite a short film and you should be able to get through it quite quickly if you know what you're supposed to know about subatomic particles and atoms and atomic symbol notation. If not, you might have to go back to your notes about those things and brush up on it a little bit. But anyway, here we go. By the end of this film, you should understand exactly what's meant by an isotope, and you should be able to use the symbol notation that we've been practicing with to describe the number of particles in isotopes. Okay, so here we go. It's really just a few examples and one really important definition. Okay, and here it is. Isotopes are, I'll read it out even though it's written on the screen, it's isotopes are atoms of the same element but with different mass numbers. Atoms of the same element but different mass numbers. Now in brackets here, what you can see is just different ways of saying what is underlined. So atoms of the same element will have the same number of protons, so I could say atoms with the same number of protons but different mass numbers. I could also say atoms of the same element but different numbers of neutrons, because if you have a different mass number you're going to have a different number of neutrons to another atom, so long as you've both got the same number of protons. Okay, so two different ways of, or more really, I suppose, lots of combinations, but to keep it simple, atoms of the same element but with different mass numbers. You can use these terms in brackets, or you go for the ones underlined. It's up to you, but remember a definition one way or another. And remember to put this word in. If you don't put atoms at the start of your definition, it's not really going to be as good. So if you just say same element, different mass number, you're not going to get the marks. Okay, so moving on with just a couple of examples, pictorially shown, first of all here. So these are three isotopes of hydrogen. How do I know that they're all hydrogen? Because each one of these atoms has got one proton, and hydrogen has an atomic number of 1. So although they hadn't written the atomic numbers in here, I could do that, but we don't need them there because we know the symbol. We're told that it's hydrogen, so we know that it's got one proton. No neutrons here, so the mass number is the same as the proton number. 1 neutron here, so the mass number is 1 greater. 2 neutrons here, so it's 2 greater. Hydrogen, this isotope is known as deuterium, and this one's known as tritium. The names aren't important, but it's important to recognize that these are isotopes of one another. Okay, helium is an element with 2 protons, so I could write the atomic number for helium every time, but I'm given the symbol, so I know there's 2 protons there. There they are, the red particles here. Okay, this isotope has a mass number of 3, so it's got 1 neutron. This isotope has a mass number of 4, so it's got 2 neutrons. Same number of protons, different number of neutrons. These two atoms are isotopes of one another. Okay, and finally lithium with 3 protons, the red ones. Not going to bother putting the atomic numbers in this time. This one's got a mass number of 6, this one's got a mass number of 7. So they've got different mass numbers but the same number of protons, so they're isotopes. Should also be able to use these things to decide what particles they were. So if someone said to me, how many neutrons are there in that substance? Well, you know it's lithium, therefore it's got to have an atomic number of 3. Take 3 from 6 and you know there's 3 neutrons, even if they hadn't drawn the little picture for you. And finally, 3 little example problems. Okay, let's write the symbols for the following things. An isotope of carbon with a mass number of 13. Well, the carbon bit shouldn't be too hard. Carbon, if we look it up, always has an atomic number of 6. Okay, this one we're told has a mass number of 13, so it's as simple as that. Okay, most common naturally occurring isotope of carbon is actually carbon-12. You might have heard the name of that come up in an earlier film. Okay, they've got different numbers of neutrons. The one we're asked about is this one. This is the one we'll see on the periodic table, but it's not the one we've been asked about in the question. Okay, isotope of chlorine with 20 neutrons. Cl is the symbol for chlorine. 17 protons if we look it up. 20 neutrons. Remember the mass number is the sum of protons and neutrons, so add 20 to 17 and the mass number must be 37. This one's a bit trickier because they've told us it in terms of electrons, so we've got to remember that the electrons in an atom will be the same as the number of protons. Okay, so we're talking about oxygen with an atomic number of 8 always. Okay, that means that oxygen has 8 electrons. It doesn't matter what isotope of oxygen we look at, it's always got 8 protons, it's always got 8 electrons. So if it's got 8 electrons and there's 2 fewer than neutrons, then there must be 10 neutrons. And if we add those 10 neutrons to the 8 protons, we've got a mass number of 18. Okay, once again, simple maths, but if you don't know the rules, you're going to find these problems hard. Even though they're simple, without the rules, they're impossible to do. So learn those rules. And the last film, really, of these films about atomic structure, in year 11 anyway, is the one about electron configurations. So that would be a good place to go next.